Welcome to the presentation of the CAiSE2020 submission Online Reinforcement Learning for Self-Adaptive Information Systems, which I submitted together with my colleagues Andreas Metzger and Klaus Pohl of the University of Duisburg-Essen. My name is Alexander Palm and I'm currently doing my PhD at the Paluno Software Institute of the University Duisburg-Essen, at which I started working in 2018. My research is basically about leveraging online learning techniques, especially reinforcement learning, to improve the adaptation logic of self-adaptive software systems. First of all, I want to quickly say some words containing the agenda of this talk. I will start by giving you a brief overview of the background and motivation of our submission to easy access to the topic. This part will include a quick recap of the topics self-adaptation and online learning, as well as a brief summary of the related work and its shortcomings, to clarify what the problem definition was and where our approach extends the current state of the art. Next, I will introduce our approach by summarizing its main concept and how they are integrated, before giving you a conceptual overview of the approach and a brief summary of our proof of concept implementation. After that, I will give you an insight into the evaluation of our approach and quickly summarize the main results. Finally, I will conclude the presentation by summarizing the limitations of our approach and giving some information about future steps. So let's start with the background and motivation of our approach. Modern information systems operate in changing context situations, which makes it difficult for them to operate as expected and fulfill their requirements at any time. To face this problem, a modern information system is enriched by the capability of self-adaptation. This enables it to adapt its own structure, parameters and behavior at runtime based on its perception of the environment, of itself and of its requirements. Examples for this are a self-adaptive online store facing different workload situations during runtime and thereby dynamically parameterizing an optional recommendation engine to maintain its performance requirements. Another example is a predictive business process monitoring system dynamically adjusting a threshold for triggering adaptations based on the current process properties. A well-known conceptual model separating a self-adaptive system into system logic and self-adaptation logic is the MAPE-K model, which can be seen on the right. Sensors are used to monitor the current behavior of the system logic and its environment, which is analyzed to determine the need for an adaptation. Next, proper adaptation actions are planned by leveraging knowledge from a so-called knowledge base before finally executing the proposed actions via actuators. However, defining an adaptation logic at design time may be infeasible due to design time uncertainties, meaning it is often not possible to foresee which environmental situations the information system will face during runtime and how adaptation decisions may impact on its quality requirements. This is where online learning comes into play, because online learning enables an information system to dynamically learn a proper adaptation logic during runtime. The most widely used online learning technique for self-adaptive information systems is reinforcement learning. Reinforcement learning, thereby, is a concept where an agent learns an optimal behavior to solve a sequential decision-making problem by directly interacting with its environment. This means it perceives an environment state and selects a proper action which leads to a new environment state. The only signal used to judge the current action selection is the immediate reward signal. Reinforcement learning solution methods can be divided into two categories, value-based and policy-based. However, all approaches of the current state of the art are using value-based solution methods, which bears mainly two shortcomings. Those approaches which use a table to store the value function need to manually quantize the state space, as self-adaptive systems typically face context situations which are perceived by continuous state variables. To fulfill convergence properties of tabular value-based solution methods, only a limited size of different states is supported. Furthermore, all value-based reinforcement learning approaches suffer from the problem that they need an explicit tuning of an exploration-exploitation parameter to ensure that all possible state and action combinations are explored to converge towards an optimal behavior based on the exploitation. For further information on this, please have a look at section 6 in our paper. Now let's go on with our approach, which solves the mentioned shortcomings of the current state-of-the-art approaches by leveraging a fundamentally different reinforcement learning method called policy-based reinforcement learning. Policy-based reinforcement learning methods differ from value-based reinforcement learning methods by not using a value function for the action selection. Instead, the parameterized stochastic policy is used, which outputs a probability distribution over the action space. This probability distribution can be used to sample a concrete adaptation action. By leveraging single experiences comprising a state, a selected action, a reward, and a successor state from a trajectory, a gradient of an objective function can be computed and used to perturb the parameters of the policy, such that the likelihood of selecting actions that led to higher rewards is increased. Now, the main idea of our conceptual approach is integrating the concept of policy-based reinforcement learning into the MAPE-K model. Therefore, the phases analyze and plan, as well as the knowledge base, are replaced by the action selection process using a stochastic policy. Now let me quickly summarize how one loop through our conceptual approach looks like. First, the current state of the system's logic and environment is monitored through sensors. The state information are then fed into an action selection component, which leverages a probability distribution computed by a stochastic policy based on the current state of the system and its environment. The sampled adaptation action is then executed via actuators. In parallel, so-called experience consisting of state information, the proposed action, a reward computed based on the fulfillment of the system's quality requirements after performing the action, and the next environment state, is used for an update of the stochastic policy by means of gradient descent. Concerning the formalization of our approach, I want to state that the underlying learning problem, which should be tackled by our approach, is formalized as a Markov decision process. A Markov decision process is a mathematical concept to define a sequential decision-making problem and comprises basically 4 components. The state space S, which is a set of states used to differentiate the different system logics and environment states. According to our approach, these states can be observed by the monitoring component via the system logic sensors. As mentioned before, in our approach, these states do not need to be manually quantized, as our approach can directly handle states composed of continuous variables. An example for such variables might be the workload of a system and its performance, for example, in terms of response time. The action space A is a set of possible adaptation actions, which can be used, for example, to change the structure of the system. Adaptation actions are executed using the system logic actuators and can be, for example, turning off or on different system features. The transition probability describes the dynamics of the environment. This means, for example, the probability of changing from one state to another under the execution of a certain adaptation action. If this is part of the environment, from the viewpoint of the adaptation logic, we do not need to have any knowledge about this function, as we leverage model-free reinforcement learning methods. The reward function specifies a numerical reward the system receives in a certain state and thereby defines a learning goal to achieve. For example, that the performance of the system should not fall below a given threshold. Finally, the solution to an MDP is called a policy, which provides a mapping from states to actions. Concerning the proof of concept implementation we use to evaluate our approach, we choose proximal policy optimization as a concrete candidate for a policy-based reinforcement learning algorithm. PPO is a model-free reinforcement learning algorithm, which means that it learns through pure interaction with the environment rather than using a model of the environment dynamics to accelerate the learning process. Furthermore, PPO is based on an actor-critic architecture, meaning it uses a policy for the action selection, but policy optimization is guided by a critic network in form of a value function. This value function is updated using bootstrapping, known from classical temporal difference learning algorithms. This enables PPO to handle continuous reinforcement learning problems, as we mostly face them in the realm of information systems. Last but not least, we choose PPO as it is said to be quite robust concerning its hyperparameters, which turned out to be true when we went with its standard parameters. Concerning the architecture of the neural network used for the actor and critic, we thereby also went with the default configuration, which was 2 layers consisting of 64 neurons each. The number of neurons in the input and output layer thereby depended on the concrete use case. As a baseline implementation of PPO provided by Google is intended to be used with OpenAI GYM environments, we set up an adapter to make our use case exemplars appear as an OpenAI GYM environment to the baseline implementation. OpenAI GYM thereby is a framework or library provided by OpenAI, providing several implementations of reinforcement learning problems. Okay, now let me quickly guide you through the results of our evaluation. Basically, we evaluated our approach by applying the proof of concept implementation to two distinct information system exemplars. The first use case system used for evaluation was a self-adaptive web application called Brownout Rubis. Brownout Rubis thereby is an online marketplace where clients can request information for certain articles. These requests can be served with recommendations about other related articles that might be of interest for the client computed by a recommendation engine. Following the Brownout paradigm, the usage of the recommendation engine is optional and can be controlled via a so-called dimmer. Finally, the reinforcement learning problem is setting the value of the dimmer in every situation in such a way that the quality requirements can be met at any time. The quality requirement in this case are avoiding the latency of user requests rising above a certain threshold while maximizing the user experience. Therefore, the reinforcement learning problem is formulated as a Markov decision process as follows. A state is comprised of the three state variables: number of requests, the monitored recommendation ratio, and the latency. The adaptation action, the dimmer value. And the reward function is defined in such a way that a maximum reward can be reached when the latency threshold is not exceeded while the recommendation ratio is maximized. Otherwise, the reward linearly decreases until it reaches zero for the case the latency is twice as high as the latency threshold. To see whether our approach is able to properly adjust the dimmer value in changing environment situations, we simulated synthetic workload following 4 different workload patterns. The learning process thereby consisted of about 4,600 learning cycles, where each learning cycle used data from 128 consecutive time steps. As can be seen on the upper left diagram for the constant workload, after an initial phase with high exploration, the dimmer value converged towards a value of 0.5 after about 2,000 learning cycles. This is done while maintaining the latency threshold of 20 milliseconds. For the off-on workload pattern, the reward increases during the first on and off phase, while the dimmer value stabilizes during the second period. During the third period, it can be seen that prior knowledge is reused to immediately set the dimmer value to a proper value. The results of the cyclic workload pattern can be seen on the lower left diagram. These results are pretty much comparable to those of the off-on workload, except that the average reward changes more smoothly. For the real workload pattern, shown in the diagram on the lower right, it can be observed that our approach is able to set the dimmer in such a way that the reward is kept around almost the same level, although the workload is nearly constantly changing. The second use case system is a self-adaptive process monitoring system. It is used to trigger process adaptations based on prediction data generated by a deep learning ensemble. Thereby, each business process consists of several checkpoints where a decision about the process adaptation can be made. At each of these checkpoints, the prediction data gives information about whether a process violation will occur or not and a reliability value for this prediction. The reinforcement learning problem is to decide for each state during a business process whether a process adaptation alarm should be triggered or not. Therefore, the underlying reinforcement learning problem is formalized as an MDP as follows. A state comprises the variables relative prefix length, defining the relative position within the process, the predicted numeric process outcome, as well as the prediction reliability. As already mentioned, the action is the triggering of an alarm for process adaptation. The reward function is specified in a way that a higher reward is given for earlier predictions. Furthermore, the adaptation decision is compared to the real process outcome and penalized if an adaptation decision was false. By applying our approach to the BPIC 2017 dataset, it can be seen that the process monitoring system is able to learn when to trigger adaptations such that the reward is maximized. During the first 250 learning cycles, the adaptation rate is very high and adaptations are triggered very early during the process. This leads to low rewards, as the accuracy of predictions used for triggering adaptations is not very high. Up to learning cycle 1250, the system learns that triggering adaptations leads to high costs and thus lowers the adaptation rate. However, this does not increase the cumulative reward as adaptations happen rather late. From learning cycle 1250 onwards, the system learned the trade-off between earliness and accuracy and thus is able to increase the cumulative reward. For further descriptions of our results, including the setup of our experiments, please have a look at section 4 of our paper. Okay, so before I close the talk, I want to briefly summarize the main limitations of our approach and point out some steps we plan for the future to extend our work. The first limitation worth mentioning is the fact that in our experience we only dealt with one single action variable. We did this to be able to better monitor the learning process and make the results more comprehensible. However, for future experiments we want to focus on use cases with a multidimensional action space. Concerning the proof of concept implementation, this should be possible in principle. Second, as mentioned during the talk, our approach is able to deal with continuous action variables as well as with discrete action variables. Despite that, considering very large discrete action spaces, for example when adapting feature-oriented or architecture-based self-adaptive systems, might be of special interest, as typically policy-based reinforcement learning methods may not be able to generalize over such kind of action spaces. Last but not least, we want to address the initial sample inefficiency of our approach. Ideas might be improving it by using an offline training phase or using policy-based implementations with a replay buffer to reuse prior experience. Okay, that's it concerning this talk. Thank you for watching this virtual presentation, and we hope that you will enjoy reading our submission to get further details.